And that is also one reason why uh, when you talk about stealth aircrafts, you don't want this reflection to be there. So generally, they nowadays they are avoiding metallic structures, not only because of weight considerations, but also because of the requirements of stealth technology. Similar to reflection, like reflection, then we are having the refraction. Okay. Like a light wave, the radio waves also get refracted, but now the refraction is due to ionization of the atmosphere. So it depends on the ionization density, and accordingly it gets refracted, sorry, and it follows the familiar Snell's law. Diffraction is same Huygens principle what you studied in your 12th standard. Uh, Here we consider a wave, EM wave, uh, to consist of some point sources, and each point source in turn can generate or propagate the radio waves. I think the next slide will be clear. Okay. You might be wondering how you receive mobile signals even when you are in the shadow zone. That is, let us say the tower is here. Okay. If you take our campus, you have the towers on the southern side. Okay, but even in W block or even in the eastern or central blocks, still you'll be getting the mobile signals. That is because of this diffraction. So at the bend, at the uh, wedge-like structures, like what you have seen in your optics, you will have some point sources. They in turn start uh, radiating. So if a receiver is, though it is kept in the shadow zone, optically it might be in the shadow zone, but still, so what I mean by optically is line of sight, there is an obstruction, but still the receiver will be able to pick up some signals, and that is due to diffraction. So basically, what it means is it follows laws of optics. The moment you make that assumption, then analysis becomes very simple. Now, the question is we talked about that Fires law in which we can estimate what will be the received power. Okay. This is the transmitter, and then the receiver is at a distance d, and we'll be able to find out what is the power received for a given transmitted power using the formulas. Now we assume that it was a straight line propagation, and we calculated this. But it might so happen that this path need not be just a straight line, it can take different forms. And those different forms are these three. First one is ground wave, second is sky wave, and third is space waves. Before I talk about it, okay. These ground waves uh, were, were the initial mode of transmission. Okay, so they use. If you look at the frequency band, it is on the MF band, medium frequency band. Though the it can go up to megahertz, you can experience this ground waves, but generally you will find that it's limited to 500 kilohertz. And as far as aviation is concerned, the only use nowadays is the non-directional beacon. We don't use it for anything else. Okay. And these ground waves or surface waves follow the Earth's curvature. So it is going to be something like this. You have an antenna, And the electric, because the antenna is vertically installed, so the electric vector is also going to be vertical. So it is vertically polarized. Now this particular electric vector will tend to follow the Earth's surface, and after some time it will die down. The mechanism is quite complicated. Okay, how it actually propagates. A very simplified model is you can assume as if initially the radiation comes out of the antenna, and then you'll have a magnetic field produced. Then this magnetic field will produce an electric vector. This change in electric vector will produce another magnetic field and so on and so forth. But for any electric current to be completed, a loop to be completed, you require the ground to be a perfect conductor. You assume that this complete thing is a conductor, which is a very crude assumption. So you assume this to be a conductor, and then it's as if this electric vector is hopping from one place to another. That's why it follows the Earth's surface. And after some time, it starts tilting. Like this angle is not perfect 90 degrees. So it goes like this, and finally it gets short circuited. So after that, you can't receive this MF wave. There are different theories about how it propagates, but they're all approximations. Uh,
Sir,
no, yeah,
if ground is perfect conductor, then ideally it will uh,
it will go for a very long distance. That is one of the reasons why this MF is very effective overseas, because sea is having salt water, right? And that can be assumed to be a conductor. Otherwise, like marshy lands, you go to Gujarat and all, those places the NDB range will be very good. In fact, Nicobar Islands, okay, you take Nicobar Islands or the Andaman and Nicobar Islands, there you get even 600 kilometers. NDB range becomes 600 kilometers. But if you go to some very dry areas like what do you say, Gwalior or Agra, where the soil is really dry, you will hardly get 200 kilometers for the same frequency and power transmitter. So this effect is quite prominent overseas. So you get really good range. Again, what do you think is the disadvantage of MF? I think we covered it in the last class. Swarup? Uh, because the frequency generally is 300 kilohertz, right? So, uh, what will be lambda?
So it will be very large, sir.
Yeah, how large?
Like
Given
so like
300,
100 meters.
10 power 3, right? 10 power
Yes,
3,
sir.
5. 10.
10.
It's 3 into 10 power 3. Huh? So it's around 3 kilometers, right? 3
It's around
kilometers, even
1 kilometer.
one tenth of it is going to be 300 meters.
Yes, sir.
That's why the antennas are quite tall. Okay, you are from Coimbatore, no? Okay. Have you traveled on the L&T bypass anytime?
Yes, sir.
Okay, just after the bridge, there is one, that Pothanur bridge. You will find a very tall mast. Okay,
Yes, sir.
that is nothing but All India Radio's MF antenna.
Okay, sir.
Though the All India Radio studio is at Ramanathapuram, the antenna is actually kept at Pothanur. And people from Chennai these MF stations are there in the marina. I exactly don't recollect which part of the marina, but it is there, and maybe Porur also it is there nowadays. I'm not very sure whether All India Radio is still operating MF bands, but these antennas are there still. What they do is generally you can't get a perfect conductor, so at least in the proximity of the antenna, what we do is see, okay, let us say this is the antenna. Uh, on the ground, we bury radial wires, copper wires, as if you want to say 100 meters. Okay. So it's as if it's a mirror sort of thing it forms. Then, if these conductors are placed properly, some improvement is got, but otherwise it's very difficult. First of all, maintaining, climbing over this antenna itself is quite an adventure. It's around 100 meters and quite a slender structure. Very few people really do it. And the worst thing is, you go to North India, people will start stealing these copper wires. Okay. Copper anyway is quite costly. So people come inside the campus and they start stealing it. After MF, the next thing which came up was the skywave propagation, which is still in use now. You radiate the signal into the upper atmosphere where it is bent back, okay, because of refraction. And refraction is basically because of the in the ionosphere where the ionization density is quite large. So depending on how the angle is, we'll get the reflection back. Now this ionosphere is something which is very unstable. Okay, this complete thing is unstable and it keeps changing with time over a period, that is diurnal variation, 24 hours, as well as seasonal variation, as well as over a period of 10 to 11 years. Any idea why it should change from 10 to 11 years? With cyclically it changes, the properties change every 10 years approximately. Yeah, anyone from the class? One is 24-hour basis, it changes. Okay. Then seasonal variation, that is 12 months cycle is there. There is also a 10-year cycle. Any guesses? Who was interested in astronomy in your class? Someone was doing, no? Or was it the other class? Not in your class, is it? You and someone, or maybe I'm getting confused with the other class.
So I think it's Astro Vicky, sir, Vignesh.
Vignesh, is it?
Yes, sir, he's interested in astronomy, I think, sir.
Okay, okay, maybe in avionics. Yeah. Okay, now you and any guesses? Why 10 years?
Uh, Not sure, sir.
Some wild guess?
Sir, depending upon the situation of the country, sir.
No, no,
Like world.
it is something which is for common to all geographical locations. But it happens every 10 years, approximately. First of all, this method of propagation should be clear. Okay, so you transmit a ray, it goes up because of the change in ionization density, just like optics where you have refraction, it comes down. Okay, it bends after some time. And depending on what angle you are transmitting, it's going to come back at that particular point. And of course, there is a region where it is you can't receive it at all. So that is called the skip distance. So the little very close to the antenna anyway there will be after the reflector. Raghavendra, no, not what Sanjay. Sorry, Sanjay. Any guesses?
No, sir. I have no idea.
What causes ionization in the atmosphere?
Ultraviolet radiation from the sun.
From the sun, right?
Yes.
Okay. Now can you put? Can you now guess what it is? It's something to do with the sun, right?
Solar flares, sir.
Uh, Solar flares are there every day, right? It's not 10 years, every 10 years. Solar flares due to something, okay? But that intensity keeps changing, right? In a cycle of 10 years. Like it's nothing, it's just the sunspot. Sunspot cycle, which is given in your +2, I don't know which thing. It is there, no? They mentioned that every 8 to 10 years, the intensity of sunspots changes. So whenever there's a sunspot, you have all these things. The ionization layer keeps changing. So we have this problem also. So because of all this variation, it's quite an uh, very unreliable method of communication, especially for aircrafts. Okay. You will see if you are listening to uh, some English song from BBC or Voice of America, then it's no issues. But definitely communication with the aircrafts is the problem. Oh, you just see the layers, how they change. This is the daytime distribution, then the nighttime. So daytime you have all this F2, F1 layers. This is all density, okay, ionization density increases at some particular place, altitude. Then you have a sporadic E layer and D layer. Uh, but when it is during nights, what happens is these F1, F2, they merge together and form one single F layer. And that is in primary mode of propagation. Getting it? Huh? So the x-axis is electron density. So depending on these density and altitude, you have different layers. Now the next question you'll ask me is how can we predict uh, these layers, the altitude of these layers? So every major nation they have something called as isosounds, and it's nothing but you transmit a pulse vertically. Okay, you transmit a pulse. This pulse goes up and then gets reflected back. So they keep on measuring these layers depending on the frequency that particular ray will come back. Okay, so if you have a frequency versus altitude, so you'll have some peaks like this, which will say that it corresponds to a particular layer. So this particular information is shared with all ATCs. and all service providers, all airlines and ATCs, they have this information with them, and then depending on the particular time, they keep changing the frequency. So generally, it is ATC to aircraft, and the two aircraft flying over oceans. Okay, especially the transatlantic flights and all those things. They depend heavily. Even now, in spite of all this advances in technology, this HF mode of communication is preferred. Now, tell me, like, what will even now? Let's say it is 3 megahertz. Okay, is the limiting frequency for HF. It goes up to 30 megahertz, but generally night time is 3 megahertz. What will be the lambda?
3 into 10 power 8, sir. 3 into 10. 6. 100, same 100 only, sir.
100, right? 100 by 10, right? Worst case.
Sir, yes, sir.
So it's 10 meters, around 30 feet. Okay. And here you can, what we practically do is any structure, any insulator, let us say generally we tie it between treetops. Okay. I have an insulator here, another insulator here, and then you tie it like this. So this particular thing will be around 30 feet. It's just a normal copper wire, and it serves this purpose. So that's it's much more easier to handle than MF. Only thing is it's extremely unreliable, and because these layers reflection depends on the height of the layers, and you have something called as daytime frequency and nighttime frequency. Daytime and probably you speak to your grandfathers, they will say that, okay, Voice of America was so and so frequency in the morning, and night it was so and so frequency. And I think once every 4 months or something, they keep changing their frequencies. They used to. Okay. Now I will use some assignment sort of thing for you people to do. Not you need not submit it at all. Just do some self study. Find out what are these terms with respect to HF communication. First is what is virtual height, what is critical frequency, skip distance. Skip distance, the name itself says, I think I already showed you the thing. And what is maximum usable frequency. And okay, how do I do it? Any NRI in this class? You want?
Sir, here only, sir.
No. Okay. Okay. Fine. Let's make a fictitious thing. We want to set up a link, HF link between Chennai and Andaman, okay, or we'll say Port Blair, and now it's on January, right? We want this link to work from January to April. So what frequencies you will select? You can take 2 weeks to go through this. Different approaches are there, different You will find a lot of resources that will keep give you some method, no one single method. We'll just discuss once, whatever you come up. And as a, it is for the complete tasking, it's not an individual task. All seven of you put together try to get some information and tell me what frequencies you'll use during this month, January to April, both daytime as well as nighttime. But what really what this slide shows is, if you look at winter and summer, whatever is this virtual height, it keeps changing. Like F2 in winter was at this level, 200 kilometers, whereas during summers it has increased to 400. So there is a lot of variation in the height. Similarly, this whatever it is, this critical frequency, try to find out what it is. You look at time of the day, how much it changes. Okay? Right from 2 megahertz and goes all the way up to uh, say 7 megahertz for particular layer. Let's assume that F2 is very prominent. So, and that also changes between winter and summer. So, what I want to emphasize is this uh, HF mode of the sky waves is extremely unreliable. Okay, you have to keep changing your frequencies depending on this term called as maximum usable frequency. So try to find out what is this MUF. Okay, you guys take 1 week. Next Monday we'll discuss on this, right?
After Pongal, sir.
I after when is Pongal? Third.
Sir, from 14th it's
How
starting.
many days holidays are you having?
5 days, I think, sir.
Starting from
14th, sir.
14th, not 13th.
Not 13th.
I thought it was 13th. Okay, 14th is Thursday. Okay, fine. Okay, then we'll do one thing, not Monday. We'll have it on Wednesday. Not this Wednesday, next Wednesday. Fine? Is it okay, Ewan? Huh? I don't want to
Okay,
trouble
sir.
you during your Pongal holidays.
Okay, sir.
Last mode of propagation is space wave, or is the direct, it's called direct wave or space wave, and it is restricted to line of sight. So as I told you, all ATC to aircraft communication, short range, is all with line of sight communication. Generally around 150 kilometers we get. Okay. If you properly sight the antennas, there's no issues. And it is VHF or UHF. So generally you will find frequencies around, if I remember right, 120 to 130 megahertz. So that is the frequency used in aviation related things. And size of the antennas definitely is going to be very small. So hardly you can say 2 to 3 feet antennas. Uh, Both the aircraft as well as on the ground, they are all small antennas. And for some confidential frequencies, we use ultra high frequencies, which is having much smaller antennas. The approximate distance which it can cover is given by this formula. So D is this complete distance from transmitter to receiver. That is in miles, and if you take h in feet, height of the transmitter and height of the receiver in feet, then you just apply this formula, you get the range of communication. So this takes into account the curvature of the earth. One can actually derive this equation quite easily. And whenever you have obstructions, you go for repeaters. So suppose the Earth's surface and antenna is here, and there is a mountain over here, and the receiver is on the other side. So what they do is they generally keep one repeater. So it receives and then transmits. Uh, this sort of arrangement is also called as transponder. Just accepts whatever is coming, doesn't process anything, and then retransmits the whole thing. Basically extends the line of sight applications. And the most common transponders are satellites. So whenever, quite often in the news, you'll find that India has hired so many transponders from something, or some other country has hired transponders from our satellite. So that's what it means. So they just receive the signal and retransmit the signal. So to sum up, three different modes: ground wave, sky wave, and space wave. This is how the uh, radio waves propagate. And for all practical purposes, whatever you people have learned in optics, those laws can be used to estimate the propagation. Along with that Fires formula, you will be able to say what is the power received for a given power transmitted. Okay. So that completes the radio wave propagation part of it. And of course, this assignment is there, which you people will have to do. Just go through the Google it, you will get a lot of information. But some information will be quite old. Okay, so you require a little bit of patience. Anything, any doubts? I'll wind up today. Next class, we'll talk about antennas. Yuvan, anything you want to ask me?
Sir, last class you asked for large frequencies how to receive signals in small antennas.
Large frequencies, yeah. Larger the frequency, shorter is the wavelength. So lambda by 10 means it's going to be very small antennas. But what was my question?
Sir, it is
Very good.
So for medium frequency, how do we reduce the length of the antenna? You said something
Okay,
about the
okay.
geometry.
It's very good. So how do I reduce it? Anything? We're able to get some clue. How do you okay? How do you put that MF antenna inside your pocket? They had a small pocket radios, right? Any clue? You got something?
No, sir.
Okay, it's plain geometry. Okay, it, the antenna theory says length should be lambda by 10. That's fine. But let us say my dimension is restricted to uh, let us say 1 feet. But I want a length of 100 feet. So how will I do it within this dimension?
Spiral it.
Good, very good. Yes, yeah, the coils. Of course, it has a lot of losses, but still it satisfies this condition. So it's called an helix antenna. Okay, so if you look closely at some of the older generation cars, if you look at that antennas, you'll find that helix. You'll have a rod sort of thing, but over the rod you will find this helix going on. Right? So that's how they were able to receive it. Okay, good. Okay then. So next class we will talk about antennas. Okay. Okay. Thanks, you. Bye.
thank you, sir.